Hi, welcome to the statics tutorials. So for this problem, we need to solve for the reactions over here at A and also at B. A is a smooth frictionless pin and B is just a smooth frictionless roller. In this one, we're also going to really focus on how we determine the directions when we're looking at our sum of the moments equation. First step though, same as always, is draw our free body diagram. So we have the shape outlined here. This pin at A is going to give us an AX and an AY. The roller at B gives us a BY only. It can't create any force in the X direction. And then we have the applied loads, the 50 Newton per meter distributed load here, the 100 Newton meter couple moment in the middle of the beam, and then we have a 50 Newton force that goes at an angle of 30 degrees up at this high end of the beam. Remember with the distributed load that the force created by the distributed load, this resultant force, is equal to the area under the distributed load. So this is a rectangular distributed load, so that area is going to be the base, so the 1 meter, times the height, which is the 50 Newton per meter. So that resultant force is going to be 50 Newton per meter times 1 meter, so just 50 Newtons. All right, let's check through our sum of forces. So sum of forces in the x direction is got to be equal to 0. That gives us AX plus the x component of that 50 Newton force. So 50 Newtons times cosine of 30. We drew AX in the positive x direction, so it's positive. The x component of the 50 Newtons is going in the positive x direction, so it's positive. And then we get a negative number for AX. That just means that in reality, this supporting reaction is going in the opposite direction, the negative x direction. But that's perfectly fine. A pin can support an x either in this direction or in that direction. Either one is good. Now let's look at our sum of forces in the y direction. So sum of forces in y is equal to 0. So we have the AY here. We also have the BY here from the support. We have the reaction resultant from the distributed load. So there's our 50 newtons, just 50 Newton per meter height times that 1 meter base. It's going in the negative y, so it's negative. And then we have the 50 newtons here times sine of 30 to give us the y component for this portion at the far end. The y component here is going up, and so it's positive in this equation. So we get AY plus BY is equal to 25 when we get done solving. And then let's do sum of moments about A. So when we do sum of moments about A, any force that goes through A can't create a moment about A. So AX and AY both go through A, and so they can't contribute any moment. Let's look at this distributed load force. So this resultant of 50 newtons sits at the centroid of the area generated by the distributed load. So the centroid of a rectangle is just going to be right in the middle of the rectangle. So instead of being 1 meter over, we'll be right in the middle. We'll be half a meter over from A. So here's our 50 newtons, which is our resultant under that distributed load, times that 1/2 a meter. Now let's take a look at the direction. So you can think about with your right hand rule, if you're at A, you try to put your fingers going in the direction of that force, and your fingers are going down in this direction. You have your thumb at A, your thumb's got to go into the board, so that's a negative force. There's no way that you can put your fingers going in this direction and have your thumb coming out of the board. The other way to think about this is just imagine that this beam is pinned here at A, and now you're pushing down on it in this direction. So if you push down on it in this direction, it would spin around in this direction like this. So imagine that this is the hand of a clock. It's going around clockwise. Clockwise is negative with our sign convention. So either way, from the right-hand rule or just thinking about clockwise or counterclockwise moments, this guy's going to have a negative sign in front of it. Let's look at our moment. So remember that a couple moment is really just two forces that are separated out by a distance. And the moment generated by that force couple is the same moment everywhere in the beam when you do sum of the moments. So even though we're over here at A, we're going to just add or subtract this 100 Newton meter in. We just need to figure out, is it positive or negative? So let's go through both of those analyses again. Let's curl our fingers around in this direction. Makes our thumb go into the board, so that's a negative moment. It needs a negative sign. Let's think about the hand of a clock sweeping around in this direction. That's a clockwise motion. Clockwise is negative. So either way, we get that negative sign in front of the 100 Newton meter force. Don't multiply that 100 Newton meter force by anything. It's already a moment. It's already in newtons times meters unit. So do not multiply it by a distance. It doesn't need it. That distance is already built in, just right in the couple itself. Now let's take a look at By. So By is the force in the y. We need to multiply it by the x distance back over to A. That's the 2 meters that we have here. Now let's try and figure out, is that positive or negative? So if we're putting our thumb at A and curling our fingers around so that our fingers go in the direction of B with our right hand, our thumb comes out of the board or out of the paper. So that's a positive moment. Again, think about this being pinned at this location that we're doing the sum of the moments, and we're going to push on this beam in this direction. This beam would spin around in this direction. That's opposite the direction of a clock's hands, so that's counterclockwise. Counterclockwise is positive with our sign convention. Either way, this By times 2 meters has a plus sign in front of it. Now let's look at probably this trickiest force up here, which is our 50 newtons. So remember that this 50 newtons has an x component here. So 50 newtons cosine of 30. And then it's got a y component here. So 50 newtons sine of 30. And let's just look at both of these. So our 50 newtons cosine of 30 is a force in the x. So we need to multiply it by a y distance. Looking back over here, our y distance back down to A is 1 meter. If it helps, you can always draw the line of action over and remind yourself that you're looking for that shortest or perpendicular distance to the line of action. So that shows you it's that y distance of 1 meter that you need to multiply by. So there's our 50 newtons cosine of 30 times our 1 meter. Now we just need to figure out the direction. So again, if we put our fingers going in the direction of that force with our right hand, our thumb's got to go into the board or into the paper, and that's a negative moment, so it needs a negative sign. Now let's think about, well, what would happen if we pin this beam here and pulled on it? Now it may be kind of hard to see because you're pulling on it way out here. Remember that when you're doing these moments, you can slide this force along anywhere on its line of action. So let's think about sliding it over to where it's just right above A, so that we have this situation. So we've got that force, and then we've got that, whoops, sorry about that. We've got that force, and then we've got that perpendicular distance. Now let's pull on that distance with that force. It's going around clockwise, and so that's also negative. Okay? So either way we think about it, it's negative in this equation. Now let's look at that last piece. So 50 newtons sine of 30 is our y component. Let's look at its line of action coming through here. This is going to be our shortest distance, is that x distance. Y force, always look for an x distance. So now, with our 50 newton sine of 30, let's apply the right hand rule. Our fingers are going up, thumbs out of the board or out of the paper, so it's positive. Now let's apply our other approach, thinking about pulling on this beam in this direction here. It's going to make it spin around in this direction. That's opposite the direction of a clock's hand, so counterclockwise, and so that's positive. We've got one equation with just one unknown, a by. We can solve it, get by is 59.2. Plug that 59.2 back into this equation that we got from sum of forces in the y, and then we got ay is equal to negative 34.2. Just as a double check, it's not a bad idea if you have a little bit of extra time. Try doing that sum of moments about b and see if you can get that same force for ay. You should be able to. You don't have to do that. But if you do sum of moments about b, it should be consistent. The result that you get should be consistent with all your other results. That's kind of a nice way to check on the homework or check on an exam question if you have time. Thanks for watching.